Hi class. Today we come to section 5.3, the fundamental theorem of calculus, part 1. So last time we was as fundamental theorem of calculus part 2, but now we come back with part 1. Okay. We actually skip 5.4. We skip 5.4. Application of fundamental theorem of calculus. But if you're interested in it, you can search in my channel to watch it. But we actually not gonna work on 5.4. So we're gonna right away come to section 5.3, fundamental theorem of calculus part 1. And the first part of a fundamental theorem deal will with a function defined by an equation of the form g of x equal to ft dt, integral from a to x of ft dt, where f is a continuous function on a to b and x varies between a and b. Okay, so let's do an example. Example 17 over here. G of x equals to the integral of ft dt from in between 0 to x. And we're going to find the value of g of 0, g of 1, g of 2, g of 3, and g of 4, and then g of 5. Then sketch a rough graph of g. Okay. So remember that's the graph. In here is the graph of f y equal to ft, not the graph of g. Okay. So according to the function, where's my? According to the function, g of x equal to the integral of ft dt in between 0 to x. So we'll just substitute in here. I know that x equals to 0, right? So I have 0 to x equals 0 of ft dt. So for this one, according to the property number 2, as in page 12, you will have this will be equal to 0. You know, just stay at 1 point. So integral will be just 0. G of 1 is actually equal to 1, so will be 0 to 1 f of t dt. Okay, now you're gonna take a look at the area under the curve from 0 to 1. From 0 to 1. Right. So now you will have what? 1/2 time with because this is area and a triangle, right? So 1/2 times base times height. So 1 and times 2. That's going to be equal to 1. Okay, so next, g of 2 is x equal to 2. So so it's going to be from 0 to 2. From 0 to 2 ft et. Right. For this one, you had to include the area from 0 to 1, which is z1, with the rectangle in the middle over here, from 1 to 2, right? So you will have from 0 to 1 integral from 0 to 1 of ft dt plus with the integral from from 1 to 2 excuse me, of ft dt, and that will give you let me put that here, 1 plus for the area from 1 to 2 is going to be an area of the rectangle. We're going to be base times height, which is 1 times with 2, and that will be equal to 1 plus 2 equal to 3. That's the answer. Okay. So we also have to find g of 3 also, right? So let's put g of 3 over here. G of 3 will be from 0 to 3 ft dt, right? And that will be that area will be includes use article over here, include from include the area from 0 to 2, and with the area under the curve from 2 to 3 over here. So let me, so then I can just write as the integral from 0 to 2 ft dt plus with the integral from from 2 to 3, right? ft dt. Okay, so you know that the area under the curve from 0 to 2 of ft dt will be 3, right? So that's going to be equal to 3 plus for the area under the curve from 2 to 3, that will be a approximate. Let me see. So for this one, for the area from 2 to 3, because I have no idea about the function of ft, but I just have to grab it, and you see in here it's the area of this under the curve from 2 to 3, that greater than the area of the triangle from 0 to 1, right? So I would say approximately it is 1.3, okay? And this is a one that I give, I'm giving you, okay? So I'm gonna say I'm giving you this approximate, okay? Approximation. Okay, so it's going to be equal to approximate equal to 4.3, right? 4.3. Okay, that is G of 3. What about G of 4? Okay, G of 4, let's use a color. G of 4 will be from 3 to 4. So G of 4 will be the area from 0 to 3, and then adding with the area from 3 to 4. So let me use alpha color. Okay, so let's say equal to from 0 to 3 ft dt, adding with the area from 0, from 3 to 4, 3 to 4 ft dt. So you can see, the area from 3 to 4 is like under the axis. So it's going to be a negative with a negative sign. Okay, so I'm going to say negative 1.3. Okay, it's negative 1.3 approximately. So then I'm gonna have this as 4.3 minus 1.3. Okay, and that's gonna be equal to 3. Go back to 3. Okay. Let's see. How can we get up? Oh, come on. Okay. Now, we also gonna find z of 5 also, right? Z of 5. So let move over here. Z of 5 here. Z of 5. And z of 5 is integral from 0 to 5. 0 to 4. ft dt plus with the interval from 4 to 5 of ft dt. You know that this according to probability number 6 of the integral. So then now let's use green one for the last area here. So that one is also a under the curve, and that should be a negative area too, right? So I will have 3, right? This is 3 minus, and approximate for 1.3. That's equal to 1.7. Okay, so again, this is approximately negative 1.3. Okay. So we're gonna look at the FT and answer the question. Say, where do we get the most area? So say, look at FT. Where do we get the most area, right? So we have, I circle the answer. So I have this one. We start with 0, right? And z1 is 1, z2 is 3, z3 is 4.3, z4 is 3, and z5 is 1.7. So So where do we get the most area? So the most area is here, right? Most area. 4/3. So which is as x equal to 3. Okay, so at x equal to 3. So x equal to 3, right? Which is that is the highest point. That is the highest, the highest point. Okay. So since you know that, yeah, since you know that, g of x, g of x graph is the entire derivative of fx. Right? So if you have 4/3 is the most area, we also give you the ft is cos x-axis, and that will give you let's say use as a color g of x over here, graph over here. We have the highest 4/3 value here. Right? I also plot some other pairs such as like 0 0, right, and then 1 1, right, and what else? 2 3, right? Plot for the g of x, right? And this one will give me 3 and 4/3, right? And then 4 and 3. And similarly, I have 5 and 1.7. Okay. So 0 and 1 1 over here. See that? I'm gonna just try to connect it. Okay. Try to connect it. Right. So look. Sure. So now you can see. Oh, come on. All right. So that is the graph of g of x. Okay. And okay. And you see that it is a called graph of all value of g. Right. Okay. Okay, so we're done with this problem, and we're gonna move to example number 18. Consider g of x equal to the integral from 0 to x of ft dt. And then we have equal to 0 of x 2t dt. So let's say number one. Or A, part A. Let's find let's find g of x. Right. Remember that g of x is the area under the curve. Y equal to 2t. Between 0 to x. 0 to x. And that will be, okay, remember that if you draw the graph of 2t, right, you should see that, because I consider just from 0 to x, so 0 should be start here. And then let's say x is here, okay? Here's x, right? So then the graph will be 2t, right? 2t is maybe up here, right? Okay. 2t is a line, so okay, so okay. So I have g equal to y equal to 2t. So here's t and here is g or y. Actually, this is y. Okay. So the graph is the area under 2t, y equal to t, in between 0 to x is a right triangle, right? So I'm gonna have 1/2 time with base times height, base x, right? And then height is it can be f of x, which is 2x. So I'm gonna write f of x, and that can be rewritten as 1/2 times x, and then times 2x. And finally, it will have x squared. Yes, squared. That's the answer. Okay. For part B, I would like to ask, what is g dv of x? Oh, what happened? G dv of x. Okay. So if I have g dv of x, I know that g dv of x will be equal to mx, right? Because g of x is entirely derivative of how can I say? No, f of x is no, g of x is entirely derivative of mx. Right? So so that's why I have g dv of x will be fx and will be equal to 2x. And then so g is the entire derivative of, oh, come on, f in this case. Okay. So could it also be the case that g of x function from the previous example is entirely with a f? So we're going to have, now we're going to have the fundamental theorem of calculus part 1. If f is continuous on a to b, then the function g defined by g of x equal to the integral from a to x of ft dt. For x is just from a to b. So this this fundamental theorem part 1 will tell you the way to convert like from uh, like a function with another variable to another variable. Okay, and it is continuous on the interval from a to b and differentiable on a to b, and g dv of x will be equal to x. Okay. Using Leibniz notation for derivative, we can write the fundamental theorem part 1 as d dx of the integral of ft dt from a to x will be equal to dx. And remember that f is continuous. Roughly speaking, if we first integrate f and then differentiate the result, we get back to the original function of f. Okay, so let's go to example 19. We're gonna find the derivative of the function gx equal to the integral from 0 to x of square root 1 plus t squared dt. Okay, so in here we're gonna say ft equal to the square root of 1 plus t squared. T squared, right? Is continuous. Okay. This function is continuous from 0 to above, right? On 0 to positive infinity. Okay. Because 1 plus t squared is always greater than or equal to 0. You know that t squared is actually it's even greater than or equal to 1. So we can apply you can use fundamental theorem. Let's notate it by FTC 1, fundamental theorem of calculus 1, part 1. Is g dv of x will be equal to fx and will be equal to square root of 1 plus x squared. Okay, so you can see up here z derivative of x will be equal to x. Okay. Okay. So now let's move to example number 20 and find d dx, the derivative of the integral from 1 to x4 cosine t t. So remember that you need you actually can right away look at this one, right, and see you know you can apply this one, but you have to watch out for in here we need to use chain rule. Okay, so let me write as careful, be careful. We need to use chain rule because limit is a function of x, which is x squared over here, x4 over here, right? Not just x. Okay. Maybe I'm gonna say here, limit is x over 4, which is a function of x. And so we have ft in here is cosine t dt, right? Oh, sorry, cosine t only. And this function is continuous on, right, from negative infinity to positive infinity, right? All remember. Okay, so we can use fundamental theorem, calculus part 1, and here g derivative of x will be equal to d dx 1 to x4 to x power 4, I mean, cosine of t dt, and equal to, let's say, d dx 1 to u. Okay, I substitute x form become u and have cosine t dt. And that I need to convert the dx over here become the u. So I have d over du of 1 to u cosine t dt. Okay, but since I know that when I convert the x to be u, I need to apply chain rule in here. That means I need to take the derivative of u, right, respect to x. Okay, so chain rule. Okay. Now, okay, don't forget to say in here, I let u equal to x4, right? move it out here. So then I have du dx will be, take the derivative of both sides, right? Yeah, I will have 4 times x to the power 30. Okay. And now I will have cosine of u for this part, right? Multiply by 4x cubed. And I may have to make this one like this. And then finally, I will substitute use at x4. And change it become cosine of x to the power 4 multiplied by 4x cubed. And that should be the answer for this part. Okay. Okay. So I will let you guys do exercise try number 17 and 18 in the class. Okay. So we will session 5.5 later.